Pile group action. Now in practice, the use of single piles are quite rare. We actually go for piles in groups, which means you have 3 piles here in this figure, which is connected at the ground level using a pile cap, and above the pile cap rests the pillar or the column from the superstructure, which means the load from the superstructure, which is transferred through the column, is taken by the pile cap and distributed to the 3 piles here. And the 3 piles will transfer or distribute the load into the soil system. Just an example, it need not be 3, it may be 2, it may be 4, etc., depending on the configurations. But anyways, the columns are usually connected and supported by 2 or 3 piles connected by the pile cap. Now these piles in a group are usually spaced at 3 times the diameter of the piles, because if they are closely spaced, their stresses will overlap, and there comes the term pile group efficiency. If you take a look at this figure, you can see that the load Q is acted upon a single pile. Now the single pile transfers its load to, let's say, an area represented like this, just like a bulb, just like the influence bulb that we have discussed, the pressure bulb. Now like that, this will have an influence zone. Now when the influence zones of these 2 piles or maybe these 3 piles are so closely spaced, there will be a highly stressed zone like this, which we have hatched. This is a figure taken from the internet, of course, but nonetheless, there's a hatched portion here, which means that the bulbs or the influence zones overlap at this portion. So once it overlaps, there's a highly stressed zone here, and it may reduce the pile efficiency. So this is the isobars drawn here, 1, 2, 3 isobars representing each piles, and you have the isobar of a pile as a group. Now this is a group of piles closely spaced. When you have them separately spaced, which means let's say more than 3.5 times the diameter spacing, each pile will have the capacity to attain its maximum load carrying capacity, which means the influence bulbs will not overlap each other and there will not be a highly stressed zone, at least theoretically, and you can actually mobilize the maximum efficiency. Now, the pile group efficiency, eta, is given by Qg by NQU. The Qg is a group capacity, N is the number of piles, Qu is the capacity of an individual pile. So of course you convert that to percentage and you get 100 to the right side. So efficiency, let's say, could be 70% in some cases, it could be 60% in some cases, etc. Now we'll discuss the group action in sand. Now the group action in sand, let's take the end-bearing pile. For a driven pile in sand, in dense sand, installed at the spacing greater than 3 times the diameter, Qg may be approximately taken as N times Qu, which means 100% efficiency when they are installed at a spacing that's greater than 3 times the diameter. Now, if the spacing is less than 3 times the diameter, the entire group is taken as a single unit and the capacity is found out. So when it's at a spacing greater than 3D, you go for this method, and if it's less than 3D, the entire group is considered as a single unit. Now in case of friction pile, for driven piles in dense sand installed at a spacing greater than 3 times diameter, efficiency is given by Fs Pgd by Nfs Pd. Now though it looks a bit complicated, it's quite simple. Fs is nothing but the skin friction, Pg is the perimeter, D is the pile depth, P is the perimeter of single pile, and N is the number of piles, which means Pg into D is nothing but the perimeter of the pile group. Let's take an example where you have 2 by 2 piles, making a 4 pile group, 1, 2, 3, and 4, right? So that pile group will have perimeter. The perimeter is Pg multiplied by the depth gives you the surface area of the thus formed group. Fs is a skin friction or adhesion in case of clay that forms a numerator. In the denominator, you take everything individually. N is nothing but 4 in the example that we have discussed now. P is the perimeter of single pile, d is the depth of a single pile, and you multiply by Fs. So this term gives you the efficiency in case of a driven piles and dense sand. You'll understand the concept much deeper when you try to do a few numerical problems in the subsequent videos. But anyways, this is the discussion on the group action in sand. Now quite similarly, you have the group action in clay. When the spacing is less than 3 times the diameter, the pile group acts as a unit, where Qg is given by Ag Qp plus alpha C Pgt. We discuss what each terms are, but when the spacing is greater, just like in the previous case, the individual capacities are mobilized, like this. In this figure you have the spacing lesser than 3D, in this figure you have the spacing greater than 3D. So when the spacing is greater than 3D, the individual pile capacities would be mobilized. So Qg is equal to N multiplied by Qu, which means individual capacities have to be summed up. Whereas in this case, you can't sum up the individual capacities because there's a stress zone there, an overlapping zone here. So you can't take the sum to arrive at the group capacity. Now, there's an equation or relation proposed by Converse-Lever equation where the efficiency of a pile group with m rows and n columns. So in this figure you can see an arrangement of piles which let's say it's in a rectangular pattern. Let's assume that in a rectangular pattern. So when this is in a rectangular pattern, you count the number of rows and you count the number of columns, just quite similar to the way the students are seated in a classroom, m rows and n columns. So when you have m rows and n columns, efficiency is given by Converse-Lever's equation as 1 minus theta by 90 n minus 1 m minus 1 n by mn, where theta is equal to tan inverse of d by s, d being the pile diameter and s being the center to center spacing. Now, this equation is an approximate method in which you can arrive at the group efficiency of piles.